कॉमा रूट 3 ओवर द फील्ड Q, डायमेंशन निकालना है।
So this is from field theory, right?
हाँ,
Okay. Q of,
रूट 2 कॉमा रूट 3
okay.
ओवर द फील्ड Q।
Hmm. You want to find this.
हाँ
This is 4.
हाँ, पर कैसे निकालो? रूट 2 तो निकाल सकते हो, पर रूट 3 एक साथ।
And you can, you have so many theorems. You have this using multiplicativity of dimension. Yeah, is this good enough? This is 2. This is not equal to 1. It is less than equal to 2. Right? So why is this not equal to 1? Why? See, this is the same as saying that root 3 is not in Q root 2. Can we prove that root 3 is not in Q root 2? Yes or no? See. And you also know that this dimension is less than equal to 2 because you already have a degree 2 polynomial. You already have a degree 2 polynomial. This is a polynomial with coefficients in Q root 2. Right? So it means the degree, so you know the degree of the extension is the degree of the minimal polynomial. Right? So you have to show that this thing is true, or you can just show that this is a irreducible polynomial, that this polynomial is irreducible in Q root 2. Not over Q it's irreducible, but also in Q adjoint root 2 it's irreducible. So you can choose either one of them and you can try to do it.
तो हमने दूसरा वाला प्रूव कर दो ना, irreducible दिखाने वाला।
Yeah, so these two are equivalent statements. right? These two are
हाँ
equivalent statements. So if if you do this without like directly going there, then I think it is easier to just prove this. Otherwise, I want to show that it is irreducible. So, sorry. Yeah, that's a good question. I actually do not know how to show such a thing is irreducible directly without going there. Because usually what happens is to show that something is irreducible, we show that, okay, the root of we say, okay, there is a root of that polynomial, and you take that root and you check its degree of extension, and you prove that the degree of extension is the degree of that polynomial, and that implies that the polynomial has to be minimal. Because if the polynomial was lesser degree, if there was a lesser degree polynomial, the degree of extension would have been lesser. So yeah, so that's okay. But if you want to show it, yeah, you just prove this. Okay, prove this. Then that implies this, because that root, just that irreducible is the same thing as whether the roots are in the field or not, because it's a quadratic, right? So just show that. And if you don't want to be more fancy, maybe let's think. Yeah. So sorry. Okay. So you see this. You think of this thing is look at it as a polynomial. Okay. And then you're looking at a polynomial in fx, and you are asking whether it is irreducible or not. And now this f is the field of fractions of this, right? If you take this and construct its field of fractions, you will get precisely this, right? So f is the, I'm sorry, f is maybe, yeah, because that's where that's the sorry, this approach is useful in many other kinds of this related questions. So this thing is a ring, and its field of fractions is q root 2. That is fine, it's obvious. And then there is the Gauss lemma, right? Gauss lemma from ring theory. What does it say? Anyone? Vaishnavi, do you know the Gauss lemma? So in ring theory, how do you show that if R is a UFD, then Rx is a UFD, right? To do these things, you have to use some Gauss lemma kind of thing, right? So anyways, I think if we say that f is monic, yeah, f is monic, okay, and f is in field of fractions of a ring R, fx, okay, then f is irreducible over this, yeah, that is the same thing as f is irreducible over R. over yeah, yeah, it's doesn't matter. But Vaishnavi, is this statement correct? Do you have seen this kind of statement?
Yeah, it's correct.
Correct, right? If you don't have monic, then it becomes a statement. You can state the Gauss lemma in many ways, but I think this is correct, and it is not difficult to prove. Yeah. So coming now to the question. So what is the upshot of all this? Upshot is we will try to then show that this in Z root 3, which eases the question because now you have a smaller domain and you want to prove something is irreducible over that. And okay, now one more question is Z adjoint root 3 a UFD? It is, right? Or yeah, I forget these things. I should not. Is it a UFD?
It's not.
It's not a UFD. Okay, well, what's the counter example?
क्योंकि we can write 6 equal to 2 into 3 that can factorize at 1 plus root 2 into 1 minus root 2.
1 plus root 2 into 1 minus root 2.
These are irreducible element in Z root 2.
Yeah, but that doesn't give you 6. Does it give you 6?
No.
Yeah, but you're right. But that doesn't work for this. That's for yeah, that counter example. Is this a UFD? I mean, if I sit down and work it out, it will come. You have to check whether it's a Euclidean domain or not. But can anyone just find it and tell quickly? Hmm. Yeah, but also it doesn't help. I think it comes down to the same check. You have to just show that yeah, that it is not in Z adjoint root 3, root 2, which is easier if you want, but it's the same thing. Okay. So I mean, yeah, you can check whether it's a UFT or not. It doesn't help much. Okay. Is there a better way? Anyone knows? There is a better way to do this question. You can think about the UFD thing later. So the problem is solved. Yeah, I cannot think of a better way. Okay. Yeah, we'll leave it there. But yeah, you can just do this, a square and so on. You just factorize. Because if it was UFD, then you would have used the rational root theorem. But it doesn't really help. Just reduces to showing that, yeah, that like yeah, the 3 is yeah, it doesn't help. Yeah. Okay, let's try some other question. The z adjoint root 2 we can think. Is there any other question?
सोमना वो वाला like
Yes.
root I mean root 3 doesn't belong to q root 2 होगा, पर उसके बाद क्या करूँ? Like इसको तो 2 दिखाना है ना, like q root 2 root 3 and q root 2 is over the field q root 2 equal to 2, वो कैसे लिखा है?
Yes, because you know it is this implies it is less than 2, right?
And where this came from?
This it is written right that the root 3, because this is the polynomial, right? This polynomial has root 3 as a root, and so
Yes.
you have a polynomial. Yes, so you have a field f and you have a polynomial of degree 2 which has that thing as a root. So the degree of the extension cannot be more than the degree of that polynomial, right?
Yes, 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 yes.
That is something which we have
Okay.
always been doing. So it's that only, and we have to use all these ideas. We have used several, like I mean, all easy. We have used the multiplicativity. We have used this theorem. We have used this thing that vector space, the subspace, proper subspace means dimension is lesser.
Okay.
These are very standard things. These examples, you have to just work it out. You should take some other examples and try. You'll find similar problems, so you should try them, practice them. Yeah.
There is a similar problem, but there is a root fourth root 2 and 2 root 2.
That will be similar, right? You should try it. You can maybe try it and later we can try. Put through.
Actually, I've seen, but it will be better
Ah.
if you show right now, please.
Oh, you have tried it?
Yeah,
But okay, so what is the question?
I have factorized it, then trying to
Okay.
find out the units and
Okay, let's see. So what's the question?
dimension of q,
Hmm.
fourth root 2 and root 2 over q. तो इसको लाइक पहले दो पार्ट में डिवाइड कर लिया, एक है कि q रूट 2 का एक्सटेंशन ओवर q, दैट इज 2, और हमें निकालना है q फोर्थ रूट 2
So
एंड
it's the
रूट 2
same
का वो
thing, right?
q
Again, you show the
हाँ,
fourth root 2 is not in Q root 2. So the degree
ऊपर
will be
वाला,
at least 2. It's the same thing, right?
तो
But
पहला वाला पार्ट.
yeah,
Yes.
so you try to show that this is an irreducible polynomial. Let's try a different way. So show that this is irreducible over Q, right? And then by Gauss lemma, this is irreducible. I'm not going to do the same way. I've already done it, and there's no point in doing the same thing again. So we'll do a different way. Yeah, we'll do a different way. So why is this irreducible?
वहाँ पे पहले फैक्टराइज कर लिया x स्क्वायर रूट 2 इक्वल टू x माइनस एंड x माइनस b करके.
No, but over
And
Q, you have to show it's irreducible. So you cannot factorize like that. You're showing over Q, right? So you should use Eisenstein's criteria, right? This you should do. Right? So what is the Eisenstein's criteria? Because you want to show it's irreducible, you want to do it in one shot. And this is a very nice look. polynomial. So what is the Eisenstein's criteria? Can you remind anyone?
That is अगर एक f इंटीग्रल डोमेन होगा तो अगर एक पॉलिनोमियल एफ एक्स बिलोंग्स टू एफ एक्स करते हैं मतलब इन कैपिटल एफ एक्स तो
F is integral
देयर
domain. Only
हाँ
integral
एफ
domain.
इंटीग्रल डोमेन
Right.
एफ इंटीग्रल डोमेन है
Yeah. Then F is irreducible.
एफ इज
If
इररिड्यूसिबल
there is a thing, right? I don't think you need monic. Or do you need monic? Just check.
मोनिक किसमें था आई गेस नो
No, yeah. I don't think. Even if you just prove it, you will see the monic not needed. Yeah. Right. And then there is something, right? P divides. No, tell me what is
ए
the.
नॉट ए वन टू एन
Mhm.
n minus 1 and p doesn't divide a n.
But what is P? P is prime.
P is prime, P is prime.
Prime in, yeah, because it's not a UFD, so but still prime makes sense. So that's a good thing. Sorry, yeah, this divides this. So you just use that, it's done, right? Because let's take 2. 2 divides 0, 2 square divides 0, whatever. But whatever, that you don't need. 2 divides all the coefficients. And 4 doesn't divide 2. That's it. Why do we learn these things? We learn these things to use these things. I mean, use in the sense that we see how it, because it's not one line, right? There are different things that can come into play. So that's the Eisenstein's criteria. Should use it. Okay, then it's 4 because the minimal polynomial is degree 4. It's irreducible, so it's minimal, right? Irreducible. So if it's an irreducible polynomial, then it's minimal, right? So yeah, and this has both these things as roots. So in one shot, you do it. Yeah. Right? So I mean, this thing, you see, this thing is same as this thing, which is, of course, there is no need to have a root 2 then, because when you have 4th root 2, you square it, you get root 2. So what are the other questions?
I have 2 right now. ये देख रहा था.
Okay. So see, whatever you've learned now when you try the problems later, you should try to apply these techniques. Okay, like this diagram, these techniques, you should try to apply, because mathematics is technical and technical, right? There is some intuition, there is some thing, but at some level it is technical. When you start the topic, even if you don't get the intuition, you have to apply the techniques and move forward. And later on, you will get the intuition. You'll know what to do. But if you don't know in the beginning, you just follow the example, follow this. But then you will soon, when you keep doing it, if you do it honestly, put the struggle and analyze. Okay, so then maybe we should just analyze this Gauss lemma, right? I just check the statement and everything. So what is the Gauss lemma? So I think there is a version which maybe we should look at, which says that so first of all, I believe that R has to be a UFD, right? One of the standard versions includes R as a UFD, right? Just correct me if I'm wrong. It might work for GCD domains also, I think. Let's see. Then you define something called the content of a polynomial, right? Content of a polynomial. And this is equal to the content of F times content of G. And what is the content? Any guesses? Vaishnavi, can you guess what should be if you don't know, can you just, based on what is going on, can you predict?
It's a GCD of the coefficient.
Okay, and what if some coefficient is 0? Do you take that or not?
Yeah.
Yeah, what should be done in that case? Do you take the non-zero? Because if you take 0, then I think you should just take it. I'm sorry, that's not a good question, right? It doesn't really change the GCD, right?
Yeah. Yeah.
It doesn't change the GCD.
Like.
It doesn't change the GCD, or does it? Does not.
No, it doesn't change it.
Right, so there's nothing to worry about. Yeah, whether you should take Z or not. So anyway, so that's fine. So we just take it. So this is the claim, and I'm not going to prove it. The proof is easy, just to do some sort of induction and so on. But it's important to understand what are these various Gauss lemmas that one hears. This is one version which you can just read the proof anywhere. It's just multiplication, but you should analyze it. I mean, if you find something that's interesting, then you should see what is it that works. Okay, but yeah, we'll not bother with that right now. But then it implies that product of primitive polynomials is primitive. Primitive is when content is 1. Right? Product, and in particular, monic polynomials are primitive because there is a 1. So when there is a 1, the GCD becomes 1. Okay. So product of primitive is primitive. Right? And yeah, anyways, you think motivation. Now, I think what it implies is F be primitive. Okay, F in Rx. Okay, what am I doing wrong? Am I okay? Let's see. The irreducible factors of F over R are same as irreducible factors of F over FR. By FR, I mean fraction field of R. Is this correct? Is this statement correct? I think we are already using the fact that it is irreducible. Sorry, that it is a UFD. Not sure if this is correct. But yeah, it is true that it's a UFD, so we can assume that, and then yeah. Yes, in this case, in that case, it should be correct, right? Right. So in particular, it implies that irreducible here means irreducible there. Okay. And how do you prove this chain of argument? How do you prove these things? I think it is just that if F is, like if F is, let's say, reducible over Rx, but if F factorizes as F1 times F2 over, I'm not doing the complete factorization, does not need it, just take a factorization and say something where F1 and F2 are not in Rx, but in FRX, then you have to get some contradiction, and it's not at all difficult, right? What you do is you do the good old high school LCM, right? You have this and you write it, and you will have some fractions because it's not in Rx, and the fractions you cross multiply, but you do it using LCM, right? And when you cross multiply using LCM, I suppose the things that you get finally, that will be a primitive polynomial, right? Because you're taking the LCM. Agree? I mean, if we've had a common multiple, then it means you didn't take the least common multiple. So it's LCM. And so it's going to be primitive and primitive. But then this side, you're going to throw up the fractions that were here. So when you take the LCM, it will be non-zero. One is there, and one doesn't affect the LCM, just like zero doesn't affect the GCD. And so you get something. And so this polynomial cannot have a content, cannot be one. But right-hand side by part 2, it has content 1. So it means irreducible here is irreducible there. And yeah, then I suppose irreducible factors are same, of course, right? If you, yeah, because that's assuming that it's a UFD, right? But I remember that this is also used to prove that, I'm sorry, it's a UFD. But yeah, you can do it. Just think about it. You because you can show that FRX is a UFD, right? Why is this a UFD? Because it's a ED. It's a Euclidean domain. You have a good old division. It's obviously a UFD because it's a PID. So it's a PID. PID is UFD. ED is a UFD. Whatever, both are fine. So that's the UFD, and because of Gauss lemma, you show that the irreducible factors are same. So in particular, they will be unique because here they are unique. So I think this is the content of the Gauss lemma, right? This seems like a summary. And if just look at it, I mean, it will not be much. It's not hard. Think it's hard, then it's hard. Otherwise, it's might not be hard actually. But just let's see what we can in common learn from the internet. Quickly, just see Gauss lemma polynomials. Yeah, and so the best written is product of two primitives is primitive. And the corollary is that is irreducible over integers. If and only if it's irreducible over rationals, then it can be generalized and do not involve existence of complete fragment. Yeah, and see, this is the guess I made. I would have read it sometime earlier, so I remember. It's true over GCD domain. So you should, Vaishnavi, you should look at it. I mean, what kind of things they're generalizing over GCD domains, because you never know. I mean, sometime you might be in a situation where GCD domains are available, but integral or sorry, UFDs are not available. It's very possible, very much possible. Yeah, this part is important to read carefully. Gauss lemma and all its consequences do not involve this. So, spine in particular polynomial over GCD domain is also a GCD. This is, yeah, so because whatever you prove using Gauss lemma, all those things will extend from the ring to its polynomial ring. All those properties, not just UFD. If one calls primitive polynomials such equations are unit ideal, the Gauss lemma remains. Right. Yes, so think about this statement. This is an interesting statement. Okay. So like you people know, right? I mean, if you have, so what is the GCD? GCD of two elements. Yeah. The GCD of two elements is by using common divisors, right? Vaishnavi, you defined it last time and you know that.
Yes,
So
yes.
it's a common divisor.
Yeah.
But you see the GCD can also be thought of as an ideal, as the ideal generated. Right? That because in a PID that actually gives you the GCD. Okay, you think, right? And but in an arbitrary ring you get an ideal which you don't know. Okay, but the ideal generated is equivalent to the concept of GCD at least for PIDs. Okay, so if you define the notion of GCD as that, then GCD being 1 would mean that the ideal is co-maximal. It generates a, so it's like you get the whole ring. For example, like you take elements and you can think, right? Ideals will generate the whole ring. I mean, generators, yeah. So that's the other version, and there also it is true. Cos lemma is true because their GCD may not exist and so on, like, so, but as they are saying that there is some problem, and that you should read, you can think about. Maybe I will not get into it at the moment. There is, because you get two different kinds of things and they are both true. Integers is fine. We should worry about more general situations. So there is a primitive part and so on, and yeah, general version. So there are more general version. Right. So these are the things. I mean, just look at it. But yeah, let's try to understand this thing at whatever level one can. So let R be a commutative ring, and then you have now you just go for general polynomials, finite many variables. Then there's a content, and you see the content is now being defined as the ideal generated by the coefficients. Okay, right? Because that's the good thing to do. That's the good thing to do. Okay. And yeah, but yeah, let's take this definition for the moment, and then you have this notion of content, and the next proposition shows this. Wow. So you see this, we have this content means ideal generated product of two ideals, and that contains the ideal generated by that, and then this is contained in the radical. So if you don't know, then read what is the radical of an ideal. This is what the geometrically nice thing is, the radical, rather than just the ideal. And so, Vaishnavi, do you see how this gives us the usual Gauss lemma for integers? Because I mean, if you just take single variable polynomial, then the content would just be the GCD, right? And the GCD would just be give you an ideal, and yeah, I don't see the other way of taking the radical. Yeah. Anyways, it should come. Anyways, we don't have time, but you should. I mean, the proofs are actually simpler as you go in this general situation. Yeah, rather than doing all the multiplication. Anyways, then let's meet on the other side, and then we'll do something, maybe field theory if there are no questions. Okay. Let's see. There should be more questions.